Hi all, this video is a conceptual video to discuss the solubility of weakly soluble ionic compounds and how we're going to characterize them with our equilibrium knowledge using a concept called the solubility product. Last semester, what we're now going to call weakly soluble compounds, last semester we would have just called that an insoluble compound. Everything in first semester chemistry is very black and white. Things are either soluble or they're insoluble. They're strong acids or they're weak acids. Here we're going to see that even things that last semester we would have called insoluble do have some small amount of solubility. We just didn't have the math yet to be able to handle to the ways to characterize them. And now we do, now that we know equilibrium. And so that's what we're going to look at. So let's imagine an experiment where you were able to monitor the concentration of both magnesium and hydroxide in a solution. So what we're going to do is we're going to put solid magnesium hydroxide in some deionized water, and we're going to monitor their concentration over a period of time. What we would see is that as time went on, we would find that both the hydroxide concentration and the magnesium concentration would grow over time. All right? Those would go up as time progressed, all right? And they would slowly approach some limit, some asymptote of concentration, all right? As that happens, if we were to look at our beaker, we would see that over time, we have less and less magnesium hydroxide. But even here, I should probably draw that with just a little more. Even here, when we reach this asymptotic point of the magnesium hydroxide, we'd still have just a little bit of it left, all right? So there's still just a little bit of remaining magnesium hydroxide, magnesium hydroxide in our beaker that's still in the solid state. However, some of it has dissolved out into the solution, and if we were to zoom in on the solution, at the particulate level, if we were to zoom in on that, we would see that there were magnesium ions floating around. We're going to make the open circles magnesium 2+ ions. Actually, no, let's make those colored in. All right. But we'd also find that there were OH ions floating around. And as will not surprise you from the balanced reaction equation, for every one magnesium, we're going to have 2 hydroxide ions floating around. Okay, that's what we would see up in the solution. Down here in the solid, the magnesium and hydroxide ions are still in their normal lattice, as we would expect for a solid. But out of the solution, they're floating around. And of course, the background here that they're floating around in is water. All right? So how do we deal with finding these concentrations where they level off? Well, it turns out that there is a way to do that using equilibrium, all right? So we're going to look at the reaction. And this equilibrium is going to be characterized by an equilibrium constant we're going to call KSP. KSP has always been my favorite equilibrium constant because SPs are my initials. But more importantly, this is a constant that is going to, what the SP actually stands for is solubility product. Okay, so this is going to be a constant that's going to characterize any ionic compound that dissolves even just a tiny little bit in water. And it turns out that pretty much every ionic compound is going to dissolve, even if it's just a tiny, tiny, tiny amount. The KSP value for magnesium hydroxide is 5.6 times 10 to the minus 12. And this is just a number that you go find in a table, or if I forget to give it to you, you look up on the internet, all right? So how do we do this? Well, as should not surprise you by now, we're going to make a rice table. All right, and initially there's no magnesium and no hydroxide dissolved in the solution. because all the magnesium hydroxide that's going to be in the solution is going to come from the solid dissolving. Now the solid has an effective concentration of 1 because its density determines its concentration. That doesn't change over the course of the reaction. We're just going to put a little squiggle there to remind ourselves that we don't need to worry about it because the concentration is just going to be 1. All right, so this is going to increase by X for magnesium and increase by 2X for hydroxide. So at equilibrium, magnesium will be X, hydroxide will be 2X. So now we're going to write a KSP expression, which is going to be, as always, products over reactants. So concentration of magnesium times the concentration of hydroxide squared. Don't forget to square the hydroxide. We have to have a square for the hydroxide because there's a 2 in the balanced reaction equation. Now we're going to take our equilibrium values and we're going to plug them into our equilibrium expression. So that's going to give that KSP, which is 5.6 times 10 to the minus 12, is equal to X times 2X squared. This always bothers people that it's both a 2X and it's squared. If you just follow the procedure and just plug the numbers in, it'll work every time. But yes, don't overthink it. Don't second guess yourself. It's okay that this is a 2X and that this is a squared. In fact, if you don't have that, you're probably wrong. All right, no, you're just plain wrong. All right, when you simplify this, be careful with the algebra. So 2X squared, the square applies to both the 2 and the X. So this is 4X squared. And then you have another X here, so that simplifies to 4X cubed. And that's all equal to 5.6 times 10 to the minus 12. All right, then you divide both sides by 4, and you take the third root to get the value of X. Now, when you do this in your calculator, there is a third root button buried in the math menu, or depending on what kind of calculator you have, it's probably buried somewhere. But the way I do it is I would type this in as, first I'm going to go ahead and do my divide by 4, just to simplify that. But now I'm going to take that resulting number and I'm going to raise it to the 1/3 power. The reason I advocate doing it this way is that while I think it's a little hokey, it always makes sure that you know how to do things like 3rd, 4th, 5th, 6th roots on your calculator. Your calculator may have a better way to do it depending on what you have, but on my TI-83, I find this is the best way to do it. Just don't forget to put your 1/3 in parentheses. All right, so caret to the parentheses 1/3, and that's going to give us a value of X of 1.1 times 10 to the minus 4. Now, what we're actually interested in here is the equilibrium concentration of magnesium and hydroxide. So the magnesium concentration is just X. That one's easy. So that's just 1.1 times 10 to the minus 4 moles per liter. Don't forget that the hydroxide is 2 times that, right? So that's going to be 2.2 times 10 to the minus 4 molar for the hydroxide. That's how we use the solubility product, the KSP, to characterize the equilibrium of an ionic compound that's dissolving into its constituent ions in water.